Hello, everyone. My name is Dr. Devon Indar, and today I'm going to be giving a lecture on flowing reactor design. Before we get started on the design equations, we'll just need to recap some definitions that you should be familiar with. And the first one is rate of reaction. We can define the rate of reaction with respect to a component I as simply the rate of change in the number of moles of that component with respect to time. However, when we're doing our design equations, you'll realize that we mostly would standardize the rate by the volume of the system. So we just standardize the rate, this one, by the volume divided by the volume. Now, we don't always have to use volume. So for example, if you're doing a catalyzed reaction, you could, in principle, standardize it by the weight of the catalyst or even the surface area of the catalyst. But for the purpose of this lecture, we'll stick to volume. You'll also need to remember your definition of conversion. So from your material and energy balancing courses, you probably would have come across conversion as moles reacted over moles fed. And if that's the case, in flowing systems, we typically give an inlet flow rate, for this case component A as FA0, outlet flow rate as FA. Then we can make the flow rate of component A and the outlet a function of conversion by simply the outlet will just be the inlet minus the moles reacted. So FA is just FA0. And to get the moles reacted, we can just multiply FA0 by XA. And we can factorize out the FA0 to give us this expression. Now, we can also express concentration as a function of conversion. And the first step in this equation is always true. The concentration of A at any given point is simply the flow rate of component A divided by the volumetric flow rate at that point. And you can double check this using your units or your dimensions, because this will be moles per second. That's the flow rate of component A divided by the volumetric flow rate, which is dm cubed per second, which will give me moles per dm cubed, which you know to be the units of concentration. But for the last step here, taking FA0 on volumetric flow rate and equating that to CA0, well, that only works if the volumetric flow rate is constant. If the volumetric flow rate is not constant, then we can't make that jump. Situations where we can assume the volumetric flow rate to be constant, well, if you're dealing with an incompressible fluid, for example, a liquid, you might be able to get away with the assumption. Also, systems where you have a negligible change in the overall number of moles. So for example, if you had a reaction A goes to B, these are in the stoichiometric ratio of 1 to 1. So for every mole of A that you consume, you form 1 mole of B. So overall, the net number of moles remains the same. But if you had, let's say, A goes to 5B, then for every 1 mole of A that you consume, you're going to form 5 moles of B. So there's a substantial increase in the number of moles here. So the volumetric flow rate will increase as you progress with this reaction. So the assumption might not be valid there. Okay, so let's get straight into the design equations. And the first reactor we're going to consider is a CSTR, or continuously stirred tank reactor. You can think of this type of reactor as simply a large, very well agitated tank. And the reaction occurs in the tank. And the key assumption in this is that the tank is perfectly mixed, so that there are no concentration gradients or temperature gradients within the tank. So everywhere inside the tank, the concentration is the same. Now, since we're drawing the product stream from the tank, then actually the product stream has the same concentration as the tank itself. What does that mean? Well, it means then that as soon as these inlet droplets here, starting off at CA0, as soon as they touch the liquid and they become instantly perfectly mixed, they immediately fall to the exit concentration. Might be easier for you to visualize in a concentration profile. So initially we're starting off here at a concentration CA0, and as soon as those droplets touch the liquid, they immediately drop all the way down to the exit concentration CA. In terms of the design equation for a CSTR, we can develop this equation using our material balance equation, which you should have been familiar with from your mass and energy balancing courses. So for a simple reaction, A goes to B. Well, we already said we're going to designate our input as FA0, the flow rate of component A entering. For a reagent, there isn't really any generation in our reaction here. A goes to B, so this is 0. We're operating at steady state, so we have no accumulation. This one goes to 0. Our output, we're going to represent that as the flow rate of component A, FA. And the consumption term, well, in this case, the rate of consumption will simply be rate in the change of the number of moles of component A. Now, we can substitute for this here using our rate of reaction definition or reaction rate. Remember that we had this definition before, so all I need to do is rearrange it to make dNA on dt the subject of the formula. And you'll see that I have a minus sign here. The minus sign is there because A is a reagent, so it is being consumed. Okay, so I've rewritten the material balance equation at the top of the page, and we can rearrange this into the form you see here. Now, typically when you're designing reactors, you want volume as a function of conversion. So what we need to do is make volume the subject of the formula, which we've done here. And we need to make this a function of conversion. So what we did was we just substituted our expression for FA being FA0 into 1 minus XA. And what you'll realize when you expand out this bracket is this minus FA0 drops with this one. So that's how we end up with this equation here. This is the design equation for a CSTR, and it is very important. It's one that you should remember. Now, an interesting quirk about CSTRs is that, remember, we assumed instant and perfect mixing. So for our concentration profile, we had entering CA0, and as soon as those droplets touched the reaction mixture, they dropped to the outlet concentration CA. And so when you're doing the design equation, you need to evaluate the rate law at the exit concentration, because that's the concentration that actually exists inside the tank. Now, suppose you had first order reaction kinetics. Let's say you're going A to B. It's an elementary reaction, we're assuming. Your rate law in that case, minus RA, would just be KCA. If we try to get a very high conversion in this reactor, well, at very high conversion, CA would fall. That means minus RA would fall. What it means then is you're going to be dividing by a very small denominator. So actually what happens is your volume is going to go up. So for these types of kinetics, if you try to achieve a high conversion, you will end up with a fairly large volume. It's not always the case, but with a lot of the kinetics, you will notice that to be true for CSTR. They tend to require a large volume. The other type of reactor we're going to consider is plug flow reactors. Now, these are a little bit different from CSTRs. You can think of these as just narrow tubes, and we're flowing our reagents through the tubes. get the name plug flow reactors because if you consider a small element within it or a differential element here, we consider this to be a plug, we assume that the plug is perfectly mixed radially. So in this direction, there is perfect mixing. But along the axis, we are allowed to have concentration gradients. So and along this way, Ca will decrease. In terms of concentration profiles, remember the CSTR1 did this. But in the plug flow reactor, it's going to look a little bit different. Said it slowly decreases along the length, so it'll do something like this. Now, let's say we have the same first order reaction going on, A goes to B. How will the reaction rates change, or how will they compare for a CSTR versus a PFR doing the same reaction? Well, in your CSTR, since the concentration of A immediately drops to the output, or the lowest value in this case, so minus Ra immediately drops to the lowest value. Whereas in your plug flow reactor, there's a much more gradual decrease in Ca. So your Ra decreases gradually. In terms of the design equation for a plug flow reactor, well, in this case, we're going to start off with a differential element within the reactor. And the differential element has a volume, delta V, which is a small volume. We're going to designate the flow rate into our differential element as the flow rate of component A evaluated at V. If you're not familiar with this bar, that just means evaluated at a point. So this is the flow rate of component A evaluated at V. And similarly, the exit is the flow rate of component A evaluated at V plus delta V. The same material balance equation applies. In this case, we just substitute in our relevant variables. The only difference here compared to the CSTR is that instead of using the total volume, since we're only considering a differential element, we need to use delta V here for the consumption term. And remember we said we typically want V as a function of conversion. And so in this format here, it's not very useful to us because this is delta V. We want to make some changes to have V as a function of X. So if you think about it, the flow rate of component A exit in the differential element minus the flow rate of component A entering is just a small change in the flow rate of component A. If you prefer a more mathematical analysis or something you might have seen before, in math, you would have probably seen something like y2 minus y1 being equal to delta y or delta y for a small change. It's the same principle here. A small change in the flow rate of component A, we'll just designate it as delta FA. Now, if we take the limit that our small differential element becomes infinitely small, then our small change in the flow rate of component A also becomes infinitely small. And in that case, our equation becomes a differential equation. And we can make our substitution for FA to make it a function of XA, which is what we want. And we can separate and integrate. We can integrate the left-hand side fairly easily because we're just integrating the number 1 dV between V and 0, so that just gives us V. And the right-hand side, you'll notice that I haven't done the integral yet. And that's because to be able to solve this, we need minus RA as a function of XA. You know, you could integrate this with respect to XA, is to have it all in terms of XA. So let's look at the two design equations. The clear difference, obviously, is that the plug flow reactor is an integral, whereas the CSTR1 is not an integral. But other than that, they are very, very similar in nature. You notice that they both have FA0 on minus RA. And the plug flow reactor is an integral with respect to XA, whereas the CSTR is simply multiplied by. Now, if we did have minus RA as a function of XA, so if we knew the rate expression or the rate law for this, we could just plug it in here and solve these things, the volumes, analytically. And that wouldn't be too much of a problem. But if we didn't have the rate expression explicitly given to us, or if we didn't know the rate expression, then what you'd have to do, you'd actually have to go into the lab and figure out how RA varies as a function of XA. With that data, suppose you knew the flow rate of the component that you were trying to process, you could come up with a plot of FA0 and minus RA versus XA. And we call that a Levenspiel plot. These plots are very useful in reactive visualization and sizing, especially when you're just getting started. So we'll analyze Levenspiel plots first and then come back to the analytical solutions after. So let's look at an experimental data set here, and suppose we didn't know the rate expression. And what we do know is FA0. And we do know that we're trying to get this up to 80% conversion. So this is XA. And the question is to find the CSTR and PFR volumes that would get us to 80% conversion. Well, as we said before, the Levenspiel plot, the y-axis is FA0 on minus RA. So to get this last column here, we just need to take FA0 and divide it by the minus RA values. And we will be able to come up with our plot. The CSTR volume, all we need to do is take the FA0 and minus RA value. Remember, we're evaluating this at the exit. And we know that the exit we're aiming for is 0.8. So we take this value and times it by the exit conversion, which is 0.8, and we get 400 dm cubed. In terms of using the graph, well, if you want to visualize what we're multiplying FA0 and minus RA, which is this length, by the XA, which is this length. When you multiply those two lengths together, what you get is the blue shaded area on the chart. Now, the plug flow reactor volume is the integral. Now, you remember from your maths, integrals of curves represents the area under the graph, the curve, sorry. So in this case, the plug flow reactor volume is the area here, the red shaded area. To find the area under this curve numerically, you can use any method that you like, one that you're familiar with. You can use Simpson's rule or trapezium rule. So in this case, if we use the trapezium rule, you'll see that the volume of the plug flow reactor that we need is 163 dm cubed. You realize that the CSTR volume is a lot bigger. This area, let me shade it in. This area here represents the extra volume needed by the CSTR to perform the same reaction to the same conversion. Now, if we knew the rate expression, then all we really needed to do was plug in the minus area as a function of XA into the design equation. And you'll remember we said that we can make this final assumption here only if the V, the volumetric flow rate, is constant. So if we have the rate expression, we just plug it in here. We plug it in here. With the CSTR design equation, there isn't any integrals to perform. You just plug it in and you get a volume coming out. For the plug flow reactor, for these kinetics, we'll have to perform the integral. The previous example that we did, this was actually done for first order reaction kinetics. And I've given you the kinetic information here. So in this case, we have the reaction rate constant. Yeah, the reaction rate constant. We know the initial concentration. We're assuming the volumetric flow rate is approximately constant. And it's valid in this case because we just have A going to B. And the stoichiometry is 1 to 1. So there will be no net change in the total number of moles in this case. So we can plug in the values and figure out that the volume of your CSTR is 400 dm cubed, which is exactly what we had from before. And when we do the plug flow reactor, our volume is 160.9 dm cubed. That's very comparable to the numbers that we had before. Remember that before we had 163 and 400. And you would expect actually that the trapezium rule would give you a slightly higher volume because sorry about that. So you can see why the trapezium rule would give us a slightly larger volume because, well, if I was to draw a large trapezium, you see that we would actually end up including a little extra volume that we didn't have from the analytical solution. So let's compare CSTRs and plug flow reactors. Well, CSTRs tend to be simpler to design and operate. You remember that we said a CSTR is simply a large, well-agitated tank. It's fairly simple to size and simple to operate, whereas a plug flow reactor, we have banks of tubes. The tubes can get blocked and the tubes can vibrate, and it's a little bit more complicated to design and operate. By definition, the CSTRs, we said that they were uniform in concentration and temperature. Due to the agitator being a very powerful unit, we have perfect mixing. Whereas in the plug flow reactor, remember we were allowed to have a concentration profile. And so therefore, there is a likelihood that you might develop what we call a hotspot. So for example, if you have an exothermic reaction, as the reagents go down the length of the plug flow reactor, you could develop a temperature gradient, and it could be dangerous if you have exothermic reactions and flammable compounds. So it's something that you really have to be careful with. Flip side is CSTRs tend to have lower surface area to volume ratios because it's just a large tank. So you can't really get as high a rate of heat transfer. If you need to get heat into or out of a CSTR, you typically either need to put a jacket around the CSTR or a coil inside of the CSTR. Whereas a plug flow reactor, it actually very closely resembles a heat exchanger. You have banks of tubes and you can flow heating or cooling medium around those tubes. So you can control the heat into or out of them a lot better. And lastly, well, for CSTRs, you're not going to be able to use a solid catalyst. We said that there's an agitator, a very powerful agitator in there. If you try to put a solid catalyst in there, the agitator would just destroy it. Whereas in a plug flow reactor, you can, and we very often do, fill the tubes with solid catalyst. And in that case, we call these packed bed reactors. Okay, so far we've considered single reactors by themselves, but what if we decide to put reactors in series, so one after the next? You'll see I have an illustration of two CSTRs in series, and the only trick here is to be careful how we define conversion. When we have reactors in series, our conversion is defined as the total moles reacted up until that point, divided by the moles fed into the first reactor. That's the only thing to bear in mind. And so, for example, if we were trying to express x2, or figure out what x2 is, mathematically, we can write this as x2. The total moles reacted up until this point, x2, would just be total moles that went in, which is FA0 minus FA2, all divided by FA0. In terms of the design equations for the CSTRs in series, well, for the first reactor, the design equation is pretty much what you saw from before. In this case, the input into the first reactor, is the input. And this is the output from the first reactor. Gives us this design equation for the volume of the first reactor. For the second reactor, our input is no longer FA0. Remember that in the second reactor now, we have the outlet from the first reactor entering. We have to make an adjustment there. So the input into the second reactor is FA1. And the output now is FA2. And you've just seen how we can define conversion at each stage to develop the design equation for reactor number 2. Now, if you look at the Levenspiel plot for our two CSTRs in series, this is the same Levenspiel plot that we had from before. And you'll remember when we did one large CSTR up to a conversion of 0.8, we needed this entire region. So we needed this purple area plus the blue plus the green. That would give us a FA01 minus RA divided by XA for one single CSTR. But if we had two CSTRs in series, the first CSTR, reactor 1, would be this blue area. So I'll just put it in a color. That would be the volume for the first CSTR, and the volume for the second one would be this. And so this purple area actually represents the volume that we saved by using two smaller CSTRs as opposed to one large one. So you might be thinking, well, if we use two CSTRs, two smaller ones, and we got some volume savings compared to one, well, why shouldn't we use three smaller CSTRs or even four smaller CSTRs? And if you push that level of thinking, then what if we had an infinite series of very small CSTRs? Would that help us a lot? Well, in that case, what we'd end up with is a Levenspiel plot closely resembling a plug flow reactor. Just need to sketch it and you'll be able to see what I mean. If I was just using 8 small CSTRs, for example, the first one would be this area, second would be this, the third would be this, and you get the idea. And the total volume of all those CSTRs would just be the areas of all these rectangles. If you're doing some calculations and for some reason the plug flow reactor design equation is too difficult for you to use, you can use an infinite sum of CSTRs to help you model your plug flow reactor design. That might be helpful later on for you. What about plug flow reactors? Is there any benefit for us in using two shorter plug flow reactors versus one long one? Well, mathematically, since dx, we're integrating minus RA with respect to XA, and this isn't going to change along the length of the reactor. So numerically, this upper limit here would just cancel with this lower limit here. And so numerically or analytically, you can see the volume would work up to be the same if we split it into two or if we left it as one. But the Leven's-field plot is a very useful tool for us to visualize. So let's make use of it. Suppose we decided to break it at 0.5, which is what we were doing before. Well, our plug flow reactor volume for reactor number 1 would be this area under the curve. And the plug flow reactor number 2 sorry, I just managed to erase the so this is plug flow reactor number 1. Our plug flow reactor number 2 would be this area here. And you can see that there would be no savings if I just sum those two together versus doing separate reactors. Now, it's not to say that you would never split a plug flow reactor into two. You'll remember we mentioned hotspots. So suppose you had a reaction that was highly exothermic and you needed some intercooling. Well, in that case, splitting your plug flow reactor would be very useful. You could stop it at a point and do some intercooling, get it all back under control, and then send it back into another plug flow reactor. So there is a reason why you might want to split your plug flow reactors. In terms of design, well, we typically want to minimize the volume of our reactors to minimize our capital cost. Usually those two parameters are directly related. So let's look at the same example, the same data set we've been doing before. And in this case, suppose you wanted to have a CSTR first that took the reaction from 0 to 50% conversion, and then a plug flow reactor from 50 to 80%. And as another question, suppose you wanted to do a PFR first from 0 to 50, followed by a CSTR from 50 to 80. Now in this case, we know the rate law. We have all the rate parameters here, so we can do this analytically. We don't need to use any numerical methods here. So when I put the CSTR first, I'll get this for part A. We'll get this blue shaded area here. And that gives me a required volume of 100 dm cubed if I was to put the CSTR first and run the reaction up to 50% conversion. But if I put a plug flow reactor first and ran the same reaction to the same final conversion, 50%, you'll see that I needed a much smaller volume, 69 dm cubed. And you can see that clearly on the graph here. This area here, that's the volume we would have saved if we used the plug flow reactor first. Similarly, when we put the plug flow reactor second here, well, the volume I'd need to go from 50 to 80% conversion is 91.6 dm cubed. Whereas if I put the CSTR second, to go from the same 50% to 80% conversion, you'll see I need a much larger volume. In this case, the volume that you've saved using your plug flow reactor is represented by this shaded region here. Furthermore, if you look at the total volume required for the system on the left-hand side, our total volume is 191.6 dm cubed. Whereas the system on the right, we have approximately 220 dm cubed. So you will see that switching around the orders of the reactors, CSTR versus PFR first, gives you different total volume requirements, which will affect your capital cost. So it's not as trivial as to say, well, usually you'd have to go through the whole process to determine what the correct staging would be for you. All the examples we've considered so far had fairly simple Levensfield plots. The reaction data was very well behaved. Let's look at an example where the data is not so well behaved. And also, let's look at an example where we solve things in the opposite order, because so far what we've been doing is we've been solving V for a given X. You've been given XA and you had to find V. What if we had to do them the other way around? Suppose we were given V and we didn't have XA, we had to calculate XA. The calculation in the reverse order is actually, well, sometimes can be more difficult than the first way around, especially if we don't have the rate law. If we don't have the rate law, then doing the calculation the reverse way around becomes a little bit more tricky, as you'll see soon. So we have this data set and we've come up with our Levensfield plot. And the question is, if we had a 200 dm cubed CSTR first, and then a 200 dm cubed plug flow reactor, what would be the conversions after each? And if we just swap the reactors around, the identical size, we're just switching the order, what would happen? Well, as I said before, if we knew the minus RA, the rate law, we could just substitute that in here, and we would be able to solve this analytically. Most students are so good at maths that I won't bother in this lecture to go through that. I want to show you how to solve the more difficult case where you don't have the minus RA expression. If you had to use the Levensfield plot or the reaction data itself to figure out the volume, your life becomes a little bit more complicated. Let's look at the CSTR, for example. We know that we need to multiply FA0 on minus RA evaluated at the exit times XA. And so suppose you just started typing in some numbers on your calculator and you tried this set of data. You multiplied 0.2 by 943 and you realized that would give you a volume of about 188.6 dm cubed. That's too small. You have a 200 dm cubed CSTR, so you decided to go one up and you tried this set of data. Well, that gave you a volume of about 254 dm cubed. That's too much. Your volume is actually 200. So in that case, what you'd have to do is you'd have to interpolate between these 2 points to figure out what your actual conversion would be. Once you figure out what your conversion would be, you could interpolate between these 2 points to find the value of your FA0 and minus RA and double check your answer. When you're doing these types of calculations, it's always important to double check your answer. Just to show you how the interpolation would work, I'm sure you're all familiar with it, but just to refresh your memories, I can put 200 minus and we would be able to solve for XA. So I've done the calculations here for you. And look at what happens if we put the CSTR first compared to the plug flow reactor first. If we put the CSTR first, we actually get to a conversion of about 22%. Whereas if you put the plug flow reactor first, you only get 18%. And you can see that right on the Levensfield plot. This area here represents, if you would use in a plug flow reactor, you would have to calculate for that area. But because of the shape of this Levens field plot, the CSTR actually gets you further for the same volume. When we put the plug flow reactor second, you'll see that overall now our final conversion ends up being about 44%. Whereas if we put the CSTR second, we only get up to 41% conversion. The plug flow reactor conversions are a little bit more tricky, and you have to be careful when you're doing these, because if your CSTR ends up at 22%, and you have to do this, well, you were doing this numerically, this first trapezium, the width here, is not the same as the width of this next trapezium, because you'll be going from 0.3 to 0.4. And if you went all the way up to 0.5, you'd realize that you ended up with a volume bigger than you had. You only had 200 dm cubed, that might give you something higher. So you'd have to interpolate again to find the exact endpoint. What I recommend you do here is you calculate the area of each trapezium separately. Because if you run the whole trapezium rule, you might end up going all the way up to wherever you decide to stop and crossing it and not know where to interpolate. But you can see that in this situation, the staging of your reactors is key. If we put the CSTR first, we get a higher conversion. Even though if the reactors are exactly the same size, the order matters a lot. As a final consideration, suppose we had the same data set, and we were trying to get all the way to the highest conversion possible, 60% in this case, or highest conversion listed. What would be the reactor combination that minimizes your overall volume? Well, if you look at the shape of the Levens field plot and you remember what the CSTR design equation was, you quickly realize that up until this minimum point, right here, if you put a plug flow reactor anywhere on this side, you would need a bigger one than if you put a CSTR. So let me show you what the CSTR would look like. So this here would be my CSTR volume. And putting a plug flow reactor anyway on the left-hand side of this minimum point would increase your volume required, because you would then have to also cater for this part of the curve. So this here is the volume that you've saved by using a CSTR first. On the right-hand side of this minimum point, everything is reversed now. Because if I tried to use a CSTR all the way up until the end, well, because you remember the design equation, I would have to cater for this plus this. So on the right-hand side of the minimum, you would find that a plug flow reactor minimizes your volume. This area on the top is the volume you've saved by using a plug flow reactor as compared to a CSTR on the right-hand side. Just switch the colors so we're all right. So this is the volume you've saved by using your PFR. On the right-hand side of the minimum. Okay, and that's it for today's lecture. If you have any questions, I'll take them now. Otherwise, thanks and have a good day.